Okay, so we're going to do an example of a standard beginning 5.3 problem. And the idea is they're going to ask you to apply the Gram-Schmidt process to a given basis. So they have to give you a basis, right? You're supposed to apply it to it. The idea is the basis they give you here is not currently an orthonormal basis, but we'd like to make it into an orthonormal basis. So we apply our Gram-Schmidt process, right? V1 is just going to be the same as the original one. Gram-Schmidt does not start by changing the first one. We leave that alone. But for your new second vector, you start with the original second vector and you subtract the projection in the direction of the first vector here. So we're going to go ahead and work this thing out. So let's see, 3, 4 minus 3, 4 dot 1, 2 over 1, 2 dot 1, 2, 1, 2. And we do this calculation here. 3, 4, and 1, 2 is going to be 11, and then 5. And we can distribute that 11/5 there. And then when we subtract, we're going to get 4/5 and negative 2/5. And so that gives us our orthogonal basis. These things are now perpendicular to each other, but they are not normalized. They are not unit vectors, which means this is not an orthonormal basis. So now we have to go ahead and make it into an orthonormal basis. And the way we do that is by taking each one of the vectors that we've got and making them into unit length by dividing by their current length. And so we get 1 over root 5 and 2 over root 5. Now for the second one, as you can see, we have fractions here, and fractions are going to be fairly common when you do this process. However, this would get really tedious and annoying. And so I want to point out a little trick to you, is that we're trying to find a unit vector in the same direction. And if you multiply or divide by a number, it's going to be parallel to the original vector. So I could choose to multiply or divide by any number I wanted to, and if I then still made it into unit vector afterwards, it will still be unit vector. So what I can do is, instead of just leaving it in term of fraction form, I could just multiply by the 5, clear out the fractions. Or, since I see a factor of 2, I can divide inside by 2. And notice that the end result that I'm going to get is going to be the same no matter what, of 2 over root 5, negative 1 over root 5. So you can kind of play around with clearing out fractions and dividing out common factors on these anytime you want to, and it's still not going to affect the process. So the final basis that we're going to end up with is 1 over root 5, 2 over root 5, and then 2 over root 5, negative 1 over root 5. And this right here would be an orthonormal basis. And that would be the answer to the question. Now, it doesn't take too much effort when you are doing a 2-vector version like this. So let's go ahead and try a 3-vector version. So let's say that my new starting basis is the following: 0, 1, 2, 2, 0, 0, 1, 1, 1. Right, so our first basis vector stays what it was. We're not going to do anything to this one here. To find our second basis vector, we start with the original second vector, and we're going to subtract off the projection here. And so that would be 2, 0, 0 minus 2, 0, 0 times 0, 1, 2 over 0, 1, 2 dot 0, 1, 2, 0, 1, 2. Now, I chose an example here that's going to work out kind of nicely, because 2, 0, 0 is already perpendicular to the vector you started with, which means that this whole second term here is just going to become 0, and I don't have to worry about doing anything. Now, that is not always going to happen. You should not expect it to happen, but when it does, it makes your life easier. Now, on your test, I'd say there's a decent chance that I'll make at least something cancel out to just make it so there's not too many alpha calculations, but who knows what it's going to be. So that means my new V2 prime happens to be the same as the original V2, but that is not always going to be the case. Then if I want to find my new V3, I take the original V3 and I do its projections in terms of the two vectors we are currently using. And again, that is the new V2. And it's important that I point this out right now because in this problem, it's going to be the same as the original V2. But in other examples, if you use the original V2, you get the wrong answer. So in general, it should be the new V2 you've gotten there. And so it's going to be 111 minus 111.012 over 012.012.012. And then minus 111.200 over 200.200 times 200. And then we just do a little bit of work here. On top there, it looks like I'd have 3. On the bottom, I'm going to have 5. Over here, I'm going to have 2 on top, 4 on the bottom, and 2, 0, 0. And so this is going to be 0, 3/5, 6/5. And this is going to be 1, 0, 0 if you work that out. And so I'd have 0, and then 1 minus 3/5 is 2/5, and that's going to be negative 1/5. And so based on this, I can also clear out the fractions, again, to make my life easier. So the three vectors I've gotten are 0, 1, 2, 2, 0, 0, and 0, 2, negative 1. There's always the last step where you make them unit vectors. It's easy to forget that on the test, so please don't do that. So I'll just make myself some room here. So again, the last step is just to take that and make them all unit vectors. So U1 is going to be 0, 1, 2 divided by the length of that. And we're going to have 0, 1 over root 5, 2 over root 5. And U2 would be the 2, 0, 0 over the square root 1, 0, 0. And U3 we get this. Okay, so this is our final basis. This is the answer to the problem. It is an orthonormal basis. I do want to make one more comment, is that if you were to try this process with a different starting arrangement of the vectors, so I could use the same three vectors, but if I put them in a different order, I can actually get different final answers. So it's going to be very important that you look at these problems in the order they give you and you work it out in the order they gave you. Otherwise, your answer might not match the back of the book when you're checking your answer. Now, hopefully you'll agree with me that this section, it's not too bad like theoretical complexity. It is long, tedious calculations though. So I don't know if that's really much better or not, but it is what it is.